All right, hey AP Chemistry. So I wanted to make the quickest video request from Jet on just how we kind of look at redox reactions and identify what's being oxidized, identify what's being reduced. So here is what's already given to you as a balanced redox reaction. All right, so I have nickel solid plus 2 Ag plus yields nickel 2 plus plus 2 Ag solid. Now, this table that I have up here are half reaction reduction potentials. This is the reduction potential for both these elements, right? So what happens when both of them are reduced, what happens to E of the cell. This is something that's going to be given to you. This is not something that you figure out. These are standard half reaction reduction potentials for these two elements, okay? Just a note, if it's more positive E of the cells, that element wants to be reduced. Element wants to be reduced. Okay? I'm making that as a note. So between these two, silver is more positive in the cell. Look at nickel. Nickel's negative. Silver has got a more positive cell potential for the reduction half reaction. That means that this reaction is more spontaneous than the reaction above. Silver will be reduced more spontaneously than nickel would, and silver would rather be reduced better than nickel. And so in looking at this, that's just an aside. Now looking at this reaction, I have nickel solid. By itself, its oxidation state is 0. I'm going to put 0. So elements by themselves are 0. I also have silver over here on the other side of the reaction. This is also 0. I have Ag plus 1. Remember, elements, if I give you their ionic charges, that's going to be their oxidation state. So silver is plus 1 over here. And then for nickel, it's nickel 2 plus. I gave you the ionic charge. That means its oxidation state is 2 plus. Okay, now I put plus 1 or 2 plus, it doesn't matter how I write it. So now if I'm looking, I went from nickel 0 to nickel 2 plus, and I went from silver plus 1 to silver 0. Going from nickel to nickel 2 plus, this is becoming more positive or less negative. This means that nickel has been oxidized. For silver, silver went from plus 1, so silver plus 1 to silver 0. This means it was reduced. It became less positive or more negative. Okay? And now how can I say less or more negative? I made a note here, like if this is 0, negative 1, negative 2, negative 3, positive 1, positive 2, positive 3. If you go from left to right in charge or oxidation state, you are becoming oxidized. Right? So silver went from positive 1 to 0. I'm going right to left. That's being reduced. Nickel went from 0 to positive 2. Nickel was oxidized. Okay? Now, if I want to write the half reactions, right? Oxidation half reaction is whichever of my species was oxidized. That was nickel. Nickel went from nickel solid to nickel 2 plus. And now, to balance this half reaction, right, I have 0 charge on the left side, and I have 2 plus on the right side. In order to balance 2 plus, I have to add 2 electrons. This is how you balance half reactions with charge, right? I add electrons to the side that's more positive, or I think about, 2 plus means I must have lost 2 electrons, okay? Same thing with the reduction half reaction. I have silver plus, aqueous, and it became Ag solid, okay? For this half reaction, I have positive 1 on the left side and 0 on the right side. I could say that I did plus 1 electron. Okay, so plus 1 means I am gaining 1 electron to become 0, or plus 1 and minus 1 gives me 0 oxidation state. So, just as a little note, to figure out how many electrons I'm adding in which way. For oxidation half reactions, electrons are always products for oxidation. For reduction half reactions, electrons are always negative. Sorry, are reactants. Reactants reduction. Okay? And the sum of all the charges needs to be the same on both sides. So to figure out how many electrons I needed to add for each half reaction, I just look at the overall charge. So again, nickel solid, nickel is 0. On the right side, we had nickel 2 plus. In order to balance this charge of 0 and 2 plus, splitting it down the middle, how can I get these both to equal the same charge? Well, we could only add electrons. So 0 and 2 plus. 2 plus 2 minus, because the 2 electrons makes them both 0. And I could say the same thing about silver. Okay, or if you don't like that method, the charge usually is equal to how many electrons I'm adding or and I follow the charge, right? So for the 2 plus, I have 2 electrons. For the 1 plus, I have 1 electron. Now, side note, in order to get these two half reactions to look like this is the balanced reaction overall, in order to get these two to look like this, I have to get that my electrons that I am adding, they have to be equal to my electrons that I'm releasing. So nickel releases or loses 2 electrons, and silver is only gaining 1. In order for that to balance, I need to find a common multiple between 2 and 1, and that is 2. Well, I already have 2 in the top part. In order for me to get 2 electrons in the bottom part, or the reduction half reaction, I multiply this whole thing by 2. So now I have 2 Ag plus, 2 electrons, and 2 Ag solid. So when I add these two reactions together, I'll add my left and right sides together. So if I add my left side, I get nickel solid plus 2 Ag plus aqueous plus 2 electrons yields Ni2 plus aqueous plus 2 Ag solid plus 2 electrons. And look at this. I have 2 electrons on both sides. They cancel out, and I get my overall balanced redox reaction. So the purpose of the half reaction is to identify what's being oxidized, what's being reduced. Sometimes you're given the half reactions, and you have to balance them just like I did to get the overall redox reaction. And then if I want to calculate E of the cell, I just want to do that last. Okay, if I want to calculate E of the cell is going to be E of the reduction, or we call that the cathode, minus E oxidation, or whatever's happening at the anode, right? And these E's that we get, these are the reduction potentials given to you in the table. So look, I have my reduction potentials up here. My E reduction potential of nickel is negative 0.25. My reduction potential of silver is 0.8. Now, my species that's being reduced is my silver. So my reduction potential I use, that's going to be, first, my E of reduction, or whatever's happening as the cathode, is going to be the silver. So E of silver minus, since silver is being reduced, nickel's being oxidized, so I'm going to have E of nickel. And so I just use these values that have been given to me since the beginning. So I'll do E of silver, which is 0.8 volts, minus 0.25 volts, right? I'm just plugging and chugging now. If I do this math correctly, I should get positive 1.05 volts, okay? Now, just a note about this E of the cell. Positive E of the cell means spontaneous. Delta G will be negative, and KEQ will be greater than 1, right? So if I have positive E cells, that means the reaction is going to happen spontaneously. It is producing a current. rather than consuming a current. This is for a voltaic cell. Okay, it's producing a current. Positive E of the cell makes the reaction spontaneous. We know that delta G will be negative for spontaneous reactions, and since it's going to be spontaneous, KEQ is going to be greater than 1. So this was kind of like a slowed down version of doing half reactions. Just in case, I'm going to do just one more, and you could look up on the table, but let's say I had the following as my half reaction. Let's say I had zinc solid plus copper plus 1 aqueous yield copper solid plus zinc 2 plus aqueous. And I'm going to say that this is not balanced. If you want, we could do a Dora the Explorer and you could pause the video. And what I'm going to say is identify the oxidation half reaction. Identify the reduction half reaction. Like what's happening. Like who's being oxidized, who's being reduced. And then I want you to balance it and give me the overall balanced redox reaction. And how would you set up solving for E of the cell? So if you want, you could try and pause the video now and then try and solve this on your own. And then I will answer the question after. Okay, so after you've paused the video and tried to do this, I'm going to look at my half reactions. I'm going to look at my reactions here. I'm going from zinc solid to zinc 2 plus. So zinc 0 to zinc 2 plus. Zinc by itself has an oxidation state of 0, and then zinc 2 plus has an oxidation state of 2 plus. Going from 0 to 2 plus means that it's being oxidized. So if I want to write my oxidation half reaction, I'm going to write zinc solid yield zinc 2 plus aqueous. And if I want to balance this, remember I said the trick is however much the charge is how many electrons there are with it, or you balance the charge. I have 0 charge on the left and I have 2 plus charge on the right. In order for me to get them both to be the same by adding electrons, I add 2 electrons to the right side. And then for copper, I go from copper plus 1 to 0. This is becoming reduced. So I'll do copper plus 1 aqueous to copper 0 solid. This is my half reaction, and if I want to balance the charge, remember, next to the charge I'm going to be putting the electrons, so that could be a trick. Next to the charge, you put the electrons. So my copper plus 1, I'm going to have 1 electron next to it. Or this left side has a plus 1 charge, and this right side has a 0 charge, so I'll have plus 1 electron. And then just like before, if I want to balance this, 2 electrons are lost in the oxidation half reaction, and only 1 electron is gained. That means I have to multiply this whole thing by 2 to get a common factor for electrons. You want to make sure that the electrons are balanced. So now I have 2 copper plus 1 plus 2 electrons yields 2 copper solid. And if I add both these half reactions together, I'll get zinc solid plus 2 copper plus 1 aqueous yields zinc 2 plus aqueous plus 2 copper solid. And notice how I didn't put in the electrons. They cancel out. You have 2 electrons on the right and 2 electrons on the left. This would be my overall balanced redox reaction. And if I wanted to calculate E of the cell, I would want E reduction, whatever's being reduced, minus E oxidation. So my species that's being reduced is my copper. So I would have E of my copper, with whatever one's the plus 1, minus E of my zinc, the one that gives me the 2 plus. All right, and there are a table of values that you will find in your textbook. You can calculate this on your own. The values that I found for E copper plus 1. For copper plus 1, it is 0.52 volts. Minus for zinc 2 plus. Zinc 2 plus, it is negative 0.76. So if I do this math, basically I'm adding 0.76 to 0.52. So I get 8, 12, 1. So I get positive 1.28 volts. Again, I have a positive E of the cell. That means delta G is going to be negative. This is going to be spontaneous. And KEQ is going to be greater than 1. Okay? So I'm hoping this very long video is helpful for you to write and balance and identify oxidation states, and write and balance and figure out what is being reduced, what's being oxidized, and then how you calculate E of the cell. You cannot do a lot of the things in Chapter 19 without doing everything that I did in this video to get E of the cell. So please make sure you watch this video critically, and this will help you be successful in Chapter 19.